last time we finished the analysis on zigzag product. So, we saw that using these 3-4 types of products, we can construct strongly explicit constant comma constant expander family, which means that the degree is constant and the second largest eigenvalue is also constant, and it is, and hence it is away from 1 via. So, spectral gap is constant, right. We saw this construction. So, that solves our one major problem. The second major problem now that we will solve using expanders is undirected graph connectivity, U path. So, we have already seen that random walk solves U path in randomized log space. So, we will now use expander construction, or we will actually use these products to show that input graph, connected graph can be made an expander, and hence if there is a path from S to T, it will become very, very small, it will become logarithmic. So, this we will achieve by various products. Okay. So, for the input graph, this lambda g may be large. We only proved a bound of 1 minus 1 over inverse poly. So, that is not good enough. So, spectral gap is 1 over inverse poly, it is not constant. So, we want to make it constant. So, to make it constant, now we will use the product systematically and increase the spectral gap to constant from 1 over inverse poly, from 1 over poly. So, from inverse poly we will go to constant. So, the thing is, the theorems you saw about spectral gap, right. So, you saw this last theorem said that if the expanders are lambda 1, lambda 2, then from that you get lambda 1 plus 2 lambda 2. So, these kind of operations will not give you inverse poly to constant. So, inverse poly will remain inverse poly. So, we actually need a different bound to achieve this. So, to make it small, we prove a different bound. Okay, let us start that. So, this is again a theorem by Reingold, Trevisan and Vadhan. And the previous estimate was by Reingold, Vadhan and Wigderson. Okay, so, that told you A B goes to A plus 2B plus B square. This will be slightly different. So, if lambda g is 1 minus epsilon and lambda g prime is 1 minus delta, then lambda of the zigzag product is epsilon delta square away from 1. Okay, so, this is the regime where now we will work. So, we will work with a g whose lambda is close to 1. So, it is like 1 minus epsilon, okay, it is epsilon close to 1 and g prime similarly. So, then or you can think in terms of the spectral gap. So, spectral gap you started with is epsilon and g prime we will use to reduce the degree. So, that has a spectral gap delta. Then the spectral gap of the zigzag product will be epsilon delta square. So, it is not immediately clear how this will help, but it will. So, let us first prove this theorem. So, basically you can think of the difference being in the earlier theorem being additive and this being multiplicative. So, the previous spectral analysis gave you this additive behavior A plus B, and what this result is giving you is in the spectral gap multiplicative, and that will somehow be helpful. Okay, let us first prove this estimate. As expected, this will go via matrix analysis. So, eigenvectors and eigenvalues and the norms, matrix norms, spectral norm that we have defined. So, let us restart. So, as before, this A zig A prime this is the normalized adjacency matrix of the zigzag product, which can also be written as, like we did before, B A hat B. So, B is the, again it refers to this inside the cloud step, then outside the cloud is A hat, which will follow the graph G, and again inside the cloud is B, which is following G prime. So, B we have seen is tensor product. Right. So, this is just a blown up version of the graph G prime, and A hat is rotation map. A prime is not A prime, A hat. A hat is the rotation map of G. Okay, so recall these three things. That is the zigzag product. Now, express A prime as A prime is this graph G prime coming from G prime, right. So, this you express as again you remember this main term error decomposition which we did in the previous proof, right. So, again think of the main term as this J by D and C as the error term with the property that J is all and C is a matrix such that its spectral norm is less than or equal to 1. So, this you can show as follows. So, recall that A prime we decomposed as lambda I Vi transpose A prime was a big D by big D matrix and its eigenvalues are lambda 1 to lambda D in decreasing order of magnitude, and Vi V1 to Vd, these are the corresponding eigenvectors which form an orthonormal basis. So, if you look at A prime minus delta J by D, okay, if you look at its action on any vector x bar, what do you get? So, this is basically 1 minus delta times C times x. So, we want to understand the norm of the matrix C. So for that we will just apply this matrix on x bar vector, and that will be, so that you can show. What do you know about A prime? You know that its second biggest eigenvalue is 1 minus delta, right? So the biggest is 1, the next is 1 minus delta, that is what you know. So you get from these two expressions, you get 1 minus delta j by d plus 1 minus delta V2 transpose, and then so on. Okay, that is the expression you get. So V1 transpose gives you j by d, and then V2 transpose, the eigenvector, corresponding eigenvector lambda 2 is 1 minus delta, and so on. So you can see that this is less than equal to, so 1 minus delta times j by d. So you remember how did we define the matrix norm in the previous proof? That is the definition of matrix norm, right? Matrix norm of A is the max of Ax by x, or in other words, the shrinkage when you multiply by a unit vector orthogonal to 1 bar. So we are taking here x bar to be orthogonal to 1. So with that assumption, j times x bar actually vanishes. So what you are left with is V2 transpose. And so on. So what can you say about this? Now this calculation also we have kind of seen before, if you recall. Again this calculation in green that we did in this slide. It's a similar calculation. Okay, so from this type of a calculation what you will get is that this is less than equal to 1 minus delta times the norm of x. Okay, so we are also using here the fact that 1 minus delta is the biggest value amongst lambda 2, lambda 3 and so on, and the remaining things cannot give you something bigger than the norm of x, where we use the fact that VI's are orthonormal bases. In particular, it means that the norm of the matrix 1 over 1 minus delta times A prime minus delta j by d, this is less than equal to 1. Okay, that is the thing we have proved. So which is why talking about C as the error term is correct, because we know that its spectral norm is less than equal to 1. Okay, so let us now begin with this decomposition, mean term plus error term decomposition of A prime, and substitute this in B. So B is equal to IN tensor A prime, which is delta j by d, which we will write as again mean term error term decomposition, right. So you get j bar delta j bar and 1 minus delta c bar. So, j bar is essentially this blown up version of j by d tensored with in, and c bar is blown up version of c tensored with in. So, remember that definition. And now we can work with m. So, m is b a hat b, b is this, then a hat, and then again. So, main term will be delta square j a j plus there are these other three terms. So, j a c, c a j and c a c. Okay, but since c is involved in them and c is kind of the error term for us, so all these three combined give a combined error term which we will write as 1 minus delta square f, where f is the remaining thing, right. So, in fact remaining thing divided by 1 minus delta square. So, I will just write it quickly. It is delta over 1 plus delta Okay, these three terms appear like this. Maybe I also write the definitions of j bar. So, j bar is in j by d and c bar is in c. Okay, so that is where we are. We have written m as main term plus error term, and error term f is just a combination of three matrices, which is and you can also see that it is a convex combination. So, the ratios are delta over 1 plus delta, the same, and then 1 minus delta upon 1 plus delta. If you sum it up, you will get 1. So, it is a convex combination of these three errors. Okay, that is also what we are preserving. And the claim here is again the norm of f is less than equal to 1. Why is that? So, it is because we have already shown that norm of C is less than equal to 1, and that would mean norm of C bar also less than equal to 1. J bar norm will depend on j by d, which you can see is also 1. Even of j it is 1, because so we have this, you can check. It is an easy check. You just have to look at j bar x for unit x orthogonal to 1. From that you will deduce this. So, both C bar j bar norm is 1, and what about A hat? So, A hat is it is a permutation matrix. So, from these three conditions you should be able to deduce, okay, that this j bar A hat C bar, C bar A hat J bar, and C bar A hat C bar, all of them have norm at most 1, and that means the convex combination also has norm at most 1. So, F has norm at most 1. So, that means M is equal to So, we further continue this breakup, mean term plus error term breakup. So, J bar A hat J bar is what? It comes from the matrix A tensor J by D. Plus 1 minus delta square F. So, lambda m which we also defined as the norm of m, spectral norm, this is less than equal to delta square norm of E tensor J by D okay, you get this. Okay. If you apply the trivial inequalities, then you will just get delta square plus 1 minus delta square, which is only 1. Okay, so that will be no fun. So what you want is away from 1, and for that you have to use the hypothesis on A. So you know that hypothesis for A is 1 minus epsilon. So use that. That will give you something non-trivial. So this is delta square 1 minus epsilon. J by D will not change it, okay. That also you can check. Plus 1 minus delta square 1. And what is this? So this is equal to 1 minus epsilon delta square. Right, that is what we wanted to show. So we have shown that this zigzag product matrix, if you start with epsilon delta, then you get to epsilon delta square. You get this multiplicative behavior. So remember that. And now using this, we can solve undirected graph reachability problem in log space. Right, I kept saying that this is main term error term, but if you carefully look at this, this term in fact is very close to 1. Okay, this is quite large. And so this is the part which is actually of interest. This is the negative part. Okay, so in fact it was the opposite. This main thing which we were trying to understand, that's the negative part. This is what tells you how much below 1 you can get. Okay, and we wanted to get this thing. So close to part 1 we have separated, that's kind of easy to handle, and the negative part is what we wanted to understand. So that we have understood to be minus epsilon delta square. So maybe that helps you in going through this proof again. Okay, so this is a simple statement, but a very advanced proof that U path is in log space. Okay, so of towns or places in a town, in a city, a big map, what this theorem is saying that even if you have a very small amount of memory, just logarithmically small amount of memory, still you can go from place S to place T. Okay, this is an amazing result. It's deterministic and it is not very old, it's relatively recent. So let G be the input graph. It is undirected, n vertex. S is the start vertex. And you are interested in the connected component of S. And the idea is that apply the graph products on G to get G tilde such that the connected component of S so basically you are moving from transforming G to another graph G tilde, which will be bigger, it has better expansion and better connectivity, and vertex S will have a, in fact for vertices S and T there will be corresponding vertices S and T in G tilde, and there will be also be a connected component of S that will be an expander. Okay, so with the lambda, which is the second biggest eigenvalue of G tilde, and D is the degree, both of them are constant. Which means, so if the degree is constant and lambda is constant, then the spectral norm is also constant. And if you recall the random walk analysis, then you know that in log n steps, n is the number of vertices in G tilde, in log n steps you will reach almost everywhere, you will reach actually everywhere with almost the same probability in G tilde, okay, in log n steps. So, which means that obviously the shortest distances in the graph G tilde, at least the connected component of G tilde, the diameter is log. In this connected component, have length at most log n. That is the key idea, that you have made the paths very small. Once the paths are very small, then you can actually, and also the degree is constant. So, you just have to guess a path in terms of neighbors doing this walk d times log n many bits. In fact, log d times log n many bits, which is constant times log n. So, this you can easily guess in log space. So, you guess it, so which means that you will actually get this path from S to T. You have solved connectivity in log space. So, all I have to do now is I have to give you the sequence of products getting you from G to G tilde. So, let D be a large constant such that d raised to 16 d 0.5 expander exists. Why these parameters? So just note that the size of the graph is quite big. It's d raised to 16. Okay, so some compared to the degree being just d. So you can actually show that if you pick d to be a big enough constant, like 10 or 20 or 30, then random graphs of this type are actually expanders, and expanders with spectral gap 0.5. Okay, so they exist. So just fix d to be such a constant. Okay, so this h is a constant sized, constant degree, constant spectral norm expander graph, which you have designed somehow, or you have just found it by a probabilistic process. So it's a one-time investment, and this is what now we will use again and again on the input graph G. So assume G to be regular. This we can assume because if it was not regular, then you can make it by these small gadgets that we saw in the very beginning. And in fact, the degree also you can make whatever you want, just at least 3. So let's make it of degree d, big D, which is d raised to 16. Okay, because as you can guess, we want to use this zigzag product with h. So h has size d raised to 16. Your graph, input graph G, has size has degree d raised to 16. So that degree will be reduced to d by when you take the zigzag product, or will be reduced to d square. So we will see that. Now transform start with the G and recursively find Gi plus 1. So take zigzag product with H. That will not really improve the expansion. So to improve expansion, you have to do path product. So do it 8 times. Okay, so that is the key transformation. Zigzag product to reduce the degree, and then path product to reduce lambda, and then again repeat the same. So let us first look at the vertices and the degree. How many vertices does GK have? So number of vertices. So GK is defined in terms of GK minus 1. GK minus 1 has degree by induction ND16K minus 1. And zigzag product with H will increase it by d raised to 16, and the path product will not change this. So that checks out. Degree of GK, again GK minus 1 zigzag H will make the degree d square. And then 8 times. Okay, so seems to be a big graph, big degree, but since d is constant, it's technically a constant. So constant times, I mean in k iterations, every time you are multiplying by a constant, so you get n times constant to the k, and that's the size, and the degree is just constant no matter what k. Now recall that for any connected graph, in fact we can also assume here without loss of generality that it's connected. Okay, just assume this because we are interested in one connected component of G. We don't care about the disconnected components. So G is a connected regular graph, and for a connected graph, recall that we have a bound for lambda. So lambda G is away from 1. G is degree D, and vertices it has is n. Where did we say that? We said it here. So for degree D and vertex n, any general connected graph, regular graph, the spectral gap is at least 1 over 8 dn cube. This we have shown before. So this comes out to be, in this case, d raised to 16 n cube. And remember that d small d is a constant, right? So this is like 1 minus 1 over n cube. So spectral gap, you already are starting with 1 over n cube, but you want to increase it to constant. So how will that be done? Let's do that. Gk minus 1 is 1 minus epsilon, then use the theorem we just proved, right? This new bound we have shown due to Reingold, Trevisan, Vadhan. So apply this on lambda of G and lambda of H. So what do you get for the zigzag product? That's the multiplicative behavior. So lambda Gk so 1 minus epsilon, there was delta square, right? So delta is half in this case, so 1 by 4, and then you raise it to 8 times because path product improves or decreases lambda by a lot, right? So you will get this. So what is happening here is when you go from 1 minus epsilon to 1 minus epsilon by 4, you went closer to 1, so which is making it worse. You get closer to 1, but then you multiply it 8 times and you are again far away from 1. Okay, so you take some bad steps, but then many good steps. That is what has happened. So let's now analyze this. So what is the spectral gap? 1 minus lambda Gk. This is at least this. So 8 times epsilon by 4 epsilon by 4 square plus dot dot, right. So, 8 choose 1, 8 choose 2 and powers of minus epsilon by 4. Then make it opposite because of the 1 minus in the beginning. So, that is 2 epsilon minus so let's write it like this. The first two terms we are looking at. So, what we see here is if we take epsilon to be small, okay, what should we compare this with? We should compare it with epsilon, right, because you started with epsilon, you started with this gap. So, let us compare this clearly with epsilon. So, 2 minus, so this is epsilon times some fraction which also depends on epsilon, but nevertheless you note that if your goal is to go above epsilon, right, you want to improve the spectral gap. So, that for epsilon less than half, the above is greater than epsilon times 2 minus 7 by 16, which is, yeah, the problem is I am ignoring the other terms. So, I have to be a bit more careful here. Anyways, so this will be increasing by a lot. So, this is something like this. Okay, so basically if epsilon is smaller than half, then this 1 minus lambda gk is a good improvement on epsilon. Okay, you started with epsilon as the spectral gap, but epsilon will be multiplied by some factor which is bigger than epsilon. So, what you learn is 1 minus lambda gk is bigger than 1 minus lambda gk minus 1 times a constant. Okay, so every time the spectral gap is improving by a constant factor and obviously greater than 1. It is always increasing. So, to go from 1 by n or 1 by n cube to a constant, it will be achievable in log n many iterations. Okay, so after you keep doing this zigzag product and path product L times, where L is log n, then the spectral gap of GL will exceed half. Okay, so lambda GL will be smaller, will be at most 0.5. That is it. So, you have made a general graph, an expander with constant parameters, constant degree, constant expansion. So, GL has log n length, shortest paths. and degree d raised to 16, which is also a constant. Okay, so now you can do path search S to T in this graph GL in log space. So, what I leave as an exercise now is do the walk in GL in log space. So, for this you have to use Reingold's recursive data structure. So, the point is that you have very little space, you have only log n space, right, but this construction that you have, the construction is Gi plus 1 is zigzag product of Gi and H. H is a constant size graph, but Gi is getting bigger. So, you have to do all these operations locally, right. You cannot store the whole thing, you do not have space or time for that. So, you have to just compute these functions in a very local way. So, you need some kind of a recursive data structure, and given that you have to do the walk. So, there is some implementation details required here. So, this is to be computed, compute only locally. And then that is possible in log space. Do not try to compute everything, because that is not possible. It is a very big graph compared to the space that you have. So, there is some technicality, data structure is to be invented and applied here, but the expander part I hope is absolutely clear. That is the main idea, to make this general graph an expander, and then the problem kind of trivializes, because the shortest paths are very short. Okay, so that finishes the topic of expanders. Okay, you can go back and read this again. These are beautiful objects. So, I hope you enjoyed this. Next thing will be in a way even more better. So, next topic or next objects that we will study are called pseudo random generators. So, we will call it PRG. So, what are PRGs? So, what was the use of expanders? Right, if you see it in terms of the use, expanders you use to de-randomize log space. And not even the whole log space, just a specific problem. So, in de-randomizing a specific problem, in RL. So, expanders are these extremely nice objects that help you in de-randomizing the random walk algorithm for a specific problem, which is the undirected graph connectivity at the level of log space. So, you can ask the question, what would it take to de-randomize all problems, right? So the whole complexity class. So PRG are objects to de-randomize general randomized algorithms. Okay, so if there is a randomized algorithm, it is asking for random bits or coin tosses, then PRG would be an algorithm. You can first think of it in terms of an algorithm or a function, easy to compute, which will simulate the coin toss very fast, efficiently, and then give this quote unquote coin toss to your randomized algorithm. Okay, and when you look at your algorithm together with this subroutine of PRG, you will see a deterministic polynomial time algorithm. Okay, so PRGs are that general. So how is such a thing defined, and what can we prove about these objects, and then can we construct these objects? So you notice that construction of expanders was not easy. Okay, this required a lot of theory, a lot of matrix analysis. That work is not yet complete for PRGs, so we don't know constructions for PRG, but there is a lot of initial theory connecting PRGs with other objects with PRG, implications of PRG, and that is what we will discuss in this chapter over the next several weeks. So first we define a distribution. So a distribution R over m bit strings is called pseudo-random. So first we define the keyword pseudo-random. So you already hopefully know what is random. Random just is it's a mathematical notion. We don't know how to do it in practice, how to implement it in practice. Although a coin toss is an approximation to that in practice. Mathematically, we just say that we have a box full of balls, and we just without looking at the balls, we randomly pick a ball. Okay, and then what is the probability of picking a certain ball? So you look at the number of favorable cases divided by the number of all cases. So it's just a mathematical formalism definition, certainly a mathematical concept. But what is the mathematical concept of pseudo-random? Right, that also, the word pseudo also we have to define. So we define it in terms of two parameters, S comma epsilon. S is the kind of the resource or the algorithmic power against which you want to prove randomness. So in our case, S will be circuit size. Epsilon will be just a fraction close to 0, denoting the error away from uniform probability. Okay, so we say that a distribution R is as epsilon pseudo random for all circuits C of size less than equal to S. The probability of Cx being 1 on this distribution, okay, versus the probability of Cx being 1 on the uniform distribution. So, what is this difference? How far is the distribution from the uniform distribution with respect to circuits of size S, right? And we are talking about Boolean circuits. This is close less than epsilon. In fact, here I will use for the uniform distribution. Okay, and so what is the idea of this? So this measures how well can C distinguish R from UM. So, is there a small circuit, by small we mean S, right, that can distinguish the distribution R from UM? If there is none, if R is indistinguishable from UM, then we call R pseudorandom. So, is R indistinguishable from UM up to small circuits? Okay, that is what this above definition means. If you are seeing it first time, it may look complicated, but there are multiple interpretations. So this is the best interpretation, that for two distributions, I mean R, for a distribution R, we'll call it pseudo random if small circuits are unable to distinguish. Okay, so this goes back to this protocol, Arthur-Merlin protocol that we studied. So essentially this R is will look random to Arthur, because Arthur will be a restricted computing machine. So maybe for Merlin it is not. Merlin will be able to distinguish it from UM, but for Arthur it will look pseudo random. So this you can think of as small, and epsilon you can think of as close to 0. It's a fraction. Okay, so based on this we will define PRGs.